I told you last time that we'll be using Venn diagrams quite a bit, and this section sort of proves that point. Most of it deals with problems where Venn diagrams are the best approach to solution. In particular, we'll be using Venn diagrams to count certain things. It's really important to get your mind thinking about these things in the right way, and I think it's very helpful if you can do so. So I thought I would try an interactive exercise to see if we can get our brains thinking about this stuff in the right way. If it works, I think it'll really make some of the exercises that might be similar to what you'll see in your homework a lot easier. So let's just jump into it. Raise your hand if you like spaghetti. Hold them up high so I can get a good count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Raise your hand if you like grits. Raise them high. 1, 2, 3, 4, 5. Finally, raise your hand if you raised your hand at least once during this exercise. Hold them high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so let's see if we can make some sense of these numbers. If you can make sense of these numbers, I think you will be getting your thought process the way you need it to be for the Venn diagram exercises that you'll see, for instance, in your homework. So let's see if we can come to grips with this number, this set of numbers. And to do so, I want to display the Venn diagram that could describe this. I have a circle S for the spaghetti lovers. I have a circle G for the grits lovers. And if you just look at it, just face on, you might say, well, 17 for spaghetti, 5 for grits. So what about 17 in the spaghetti circle, 5 in the grits circle? Any comment about that? Does that look right? What do you think? Exactly. We're not considering the overlap, the people that like spaghetti and grits. Just looking at those numbers, is there a way to figure that out? Just think about it a minute. 17 and 5 is 22, but only 18 of you said that you raised your hands at least once. 18 from 22 is 4. Doesn't that imply that 4 of you liked grits and spaghetti? So that tells me that I should have a 4 in the overlapping region between spaghetti and grits, and that those numbers that I wrote in earlier, 17 and 5, are not right. What I want is for all the numbers together in the spaghetti circle to add to 17. So if I have 4 in the overlapping area, that means I need 17 minus 4. I need 13 more in the part of the spaghetti circle that I had earlier labeled 17. So not 17. I want 13 and 4 to add to 17. Similarly, for the grits circle, I don't want that 5 there because 4 people like grits and spaghetti. I want the grand total in the grits circle to be 5. So 5 minus 4 is 1. There's one person unaccounted for that likes grits but does not like spaghetti. And to see that that sort of all the counting works out, if you take 13 plus 4 plus 1, you get 18, and that matches the number of people who raised their hand and said that they raised their hand at least once during this exercise. So I don't want to do anything else with this exercise. It's just a simple illustration of the sort of thought processes that are going to help you when you get to the real homework problems. I told you at the beginning that this section was mostly Venn diagrams, and that is true. However, I do want to say there are ways around Venn diagrams in fairly simple situations that might be worth knowing about. You could still do it with Venn diagrams, but maybe something else is better, and that's what I'm going to suggest here. In certain situations, even though Venn diagrams work, you might be better off doing it this way. It's something that your text calls the inclusion-exclusion principle. The idea is simple, and I'll try to make you believe that, but I'll read it first. It says, for all finite sets A and B, do you remember what this notation means? This little n with parentheses, with something inside the parentheses. Anybody remember what that means? I'll give you a hint. It starts with n. What? Did I hear somebody say something? It starts with an n. It ends with r, the first word. It starts with nu, ends in an r. It starts with num and ends in an r. Number. Thank you. That symbol stands for the number of something. So it's the number of things in the union of A and B. So the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. Think about the spaghetti and the grits. I was asking at one point how many people like spaghetti or grits. You would count the number of people that like spaghetti, then you'd count the number of people that like grits, and we ended up having to subtract because some people liked both. When you say the intersection of two sets, you're counting the overlap. So that's like, if you think of that as spaghetti and grits, you're counting how many people like spaghetti, you're counting how many people like grits, and we realized the number was too big because some people like both, and you have to subtract off the one you counted twice. You ended up counting the people that like both twice. So that intersection number is just an indication that you counted it twice, so you need to subtract off one of the counts. And that's all the inclusion-exclusion principle says. If you compute the number of elements in the union of two sets, you just need to add up how many elements are in each set, and then you take off the numbers you counted twice. That's all it says. The number of elements in the union of two sets is the number of elements in each set individually added up minus the number of elements that are in common to both. So rather than formally memorizing that, I just remember the words. If you're really good at memorizing formulas, then go for it. But I like to memorize the words. I like to say it to myself. And sometimes you'll find that inclusion-exclusion principle will save you from having to draw a Venn diagram when they're asking about things involving the union of two sets. And I'll show you an example. I'll actually show you probably more than one example, but I'll start off with a really simple example. Suppose I have a Venn diagram with the set A and the set B in it. How many elements are in set A? 8. How'd you get that? Yeah, there's 6 that are in A and not B, and there are 2 more that are in A but also in B. How many elements are in set B? 6, right? Well, 8 and 6 is 14, but obviously that's too big, because if you add 6 and 2 and 4, you only get 12. Well, that's because even though you have 8 in set A and you have 6 in set B, and 8 and 6 is 14, you realize you've counted 2 of them twice, so you have to subtract off one of the double counts. So 8 and 6 is 14 because you've got 8 here and 6 here, but you realize you've counted 2 twice. So you have to subtract off one of those double counts. That's all it says. Simple idea, but it can be useful. Let's try this one. Given the number of elements in set S equals 170, the number in set T 140, and the number in the union of S and T equal 220, find the number of elements in the intersection of S and T. Using the inclusion-exclusion principle, we know that the number of elements in S union T is 220. the number of elements in set S is 170, and the number of elements in set T is 140. If we plug those things in, you see that there's only one unknown, and that is the number of elements in S intersect T, which is what we're trying to solve for. So now it becomes a simple algebra problem. 170 plus 140, of course, is 310. If you move the negative number of elements of S intersect T to the left side of the equation and move the 220 to the right, you'll end up with the number of elements in S intersect T is 310 minus 220, which is 90. Let's try another. If we're given that the number of elements in set A is 1500, the number of elements in set A union B equals 2250, and the number of elements in the intersection of A and B is 310, find the number of elements in set B. Again, we're using the inclusion-exclusion principle, but this time we're looking for the number of elements in set B. So if you plug in everything you know, the number of elements in set B is the only thing you don't know, so that's your unknown. You can leave in the number of elements in set B as your symbol, or you could plug in a variable like X. In any case, 1500 minus 310 is 1190, and if you subtract 1190 from both sides, you'll find out that X is equal to 1060. That is the easiest way to solve this problem. If you wanted to play around with Venn diagrams, you could get the same solution, but I think this is easier. If you did do this with Venn diagrams, you would end up with something like this. I don't really advocate that you do it that way, but you could. Here's another problem where you could use a Venn diagram, but it's much simpler to use the inclusion-exclusion principle. It says a music director wishes to take the band and the choir on a field trip. There are 65 students in the band and 30 students in the choir. The number of students in both the band and choir, in other words, some people are in both, is 16. How many students should the music director plan on taking on the field trip? In other words, the music director needs probably to get a bus to take people, so how many people need to be on a bus is an important number. Well, this has to do with taking band members or choir members, and that's a union. Whenever you say or, you mean union. Whenever you say and, you mean intersection. So we want to know, we want to count people that are either a band member or a choir member. So the trick is to remember, whenever you're doing an or, that's the same as a union. Well, as soon as you're looking at the union of two sets, you know you can use the inclusion-exclusion principle. So you say, well, I can count how many band and choir people there are. I can count the band people, then I can count the choir people, and then I can subtract off the ones I counted twice. Well, there are 65 band students, 30 choir students, and there were 16 that got counted twice. And so if you subtract 16 from the sum of 65 and 30, you end up with 79. And that tells you have 79 students that you need to plan on taking with you. And again, you could draw Venn diagrams and figure it out, just like we did the grits and spaghetti thing. You could figure it out, but it's just much more straightforward to do it that way. Tired of doing music problems. Let's do something that's got math in it. This time we have a school that has 430 students registered in math, 560 students registered in chemistry, and 225 are taking both. How many students are registered in math or chemistry? In other words, you don't want to count people twice. So this again is an or, which is a union, which kind of lets you know that you might be able to do it with the inclusion-exclusion principle. And again, you could draw Venn diagrams and figure it out if you wanted to. But the inclusion-exclusion principle says to find the number of people that are taking math or chemistry. You count the number of people that are taking math, the number of people taking chemistry, add those up, and then subtract off the intersection, which are the people you've counted twice. So that would be 430 taking math, another 560 taking chemistry. You've counted 225 of them twice, So you end up with 765 unique students. So that's the nice thing about the inclusion-exclusion principle is it's actually, if it applies, really quicker than trying to figure it out with Venn diagrams. Whereas some of the more complicated problems that have 3 circles and have all these things going on, you pretty much have to do a Venn diagram. But when it's simple like that and you're just looking at a union problem with 2 sets, think about doing it this way. It just seems to be simpler. I just want to throw in that if the number is a percent, it still works. I don't know if I even need to say that, but I just wanted to throw in that if it works with 17 and 32 and whatever, if I put a percent sign and say 17%, 32%, it still works. So I'm just throwing that out there that if they put a percent sign on a number, it still the principle still works. Here's an example of something like you might say on your homework. It says a blood donation organization reports that about 44% of the U.S. population has the A antigen. Another 15% of the U.S. population has the B antigen, and 4% have both. They even did a pie chart. The question is to estimate the percent of the U.S. population that has the A antigen or the B antigen. That's A union B. Remember, or is union. Union of 2 sets, if you're counting, you can use the inclusion-exclusion principle. So that's what I would do. The percent of people that have the A or the B, that's percentage of people having either the A or B antigen, is the percentage of people with the A antigen plus the percentage of people with the B antigen minus the intersection. In other words, the people that have both the A and the B antigen, because you've counted them twice. They tell you that 44% of the population has the A antigen, 15% of the population has the B antigen, and 4% has both the A and B antigen. That means they're an AB type. If you have the A antigen and the B antigen, you're an AB. And if you calculate that, that's 55. Now, I'm a big proponent, especially on a test, of having a second way to check your answer. Because they gave you the pie chart, you could check your answer by doing it in the pie chart and see if you get the same thing. So we're trying to count the people that have either A or B or both. So if you just look at that, this 1% has the A and the B. That's A or B, and that's A or B or both. The AB positives have A or B. They actually have both. The B has a B. There's a B positive, a B negative. There's an A positive and A negative. And if I counted B positive, B, I think so. If you add up those numbers I circled, you should get 55 unless I skipped one. So if you take 34 plus 6, that's 40. That's 42. That's 45. That's 46. What have I missed? Oh, I didn't count the B plus. 46 plus 9 is 55. In this problem, we're given a Venn diagram with circles A, B, and C. And we're told that the number of elements in set A is 29, the number of elements in set B is 33, the number of elements in set C is 38, the number of elements in A intersect B is 16, and the number of elements in the universal set is 78, and they want us to find those numbers R sub 1 through R sub 5 in the Venn diagram. Notice they've given you a lot of the information in the middle part of these. When we're starting from scratch on these, we typically go for the dead center, so that value of that where there are 3 elements. Generally, we would start there, but they've already given it to us. Looking back, the most specific information that they actually gave us was the fact that the number of elements in A intersect B is 16, and that represents what I typically call a football shape. It's the intersection of set A with set B. That's supposed to be 16, but there are already 3 elements in there. So if you do a little algebra, you'll find out that the number of elements in the region represented by R sub 2 must be 13, because 13 plus 3 is 16. Once you get that, you notice that you know every value inside of circle A except for R sub 1, and you know from above that the number of elements in set A is 29. So you can use that fact to add up all the elements in set A and figure out what R sub 1 must be. It turns out that 13 plus 3 plus 7 is 23. So R sub 1, the number of elements in that region R sub 1, must be 6. And you keep doing that. Now you go to circle B, and you see that those numbers have to add up to 33, meaning that R sub 3 must be 12. And finally, circle C, and you add up all the numbers in circle C, and you figure out that the number of elements in the region R4 has to be 23. And finally, you know that there are 78 elements in the universal set, so if you add up every number in the rectangle, that has to come out to be 78. And if you do the arithmetic, you'll find out that the number of elements in that R sub 5 region must be 9.